Hello and welcome to the Momentum and Impulse unit of Phys 1101. And what momentum and impulse are particularly useful for is analyzing collisions. So that's where we're going to start. Up until now in the course, we've been using forces to find accelerations. And well before we had encountered forces in the course, we knew how to use accelerations to predict the subsequent motion of an object. But the methods we've been using really only work if our accelerations are constant, and that's only true if the forces are constant. Now you can use these methods when you have varying forces, but you need calculus to do it, and we're not using calculus in this course. Even if you do know how to use calculus, though, often there are quicker and easier ways than working through all this with calculus. So in the next part of the course, we're going to look at approaches for dealing with varying forces. And this is a real change for us. Up until now, we've been using acceleration, which is a rate of change of velocity, to talk about velocity, which is a rate of change of position. And so we've been very concerned with how things change. But the unifying idea in this next part of the course is conservation laws. And what this means is that we're looking at quantities that don't change, even when other things are changing. And it turns out that from things that don't change, you can often figure out a lot about the other things that are changing. Before we move on, I just want to take a moment for a digression, because what we're getting into here is something much closer to the way physicists today understand the conceptual underpinnings of physics. And it goes back to some work by a woman who is probably the most important mathematician you've never heard of. Her name was Emmy Noether. And she came up with this theorem, which applies to Newtonian mechanics, which we've been studying, and it also applies to quantum mechanics, which is kind of important. And basically, in brief, what her theorem says is that symmetries correspond to conservation laws. Now, that probably doesn't mean very much to you, so let me illustrate. We know that Newton's second law works. We also know that you can set your axes anywhere you want. Well, the fact that Newton's second law doesn't change when you move your axes turns out, through Noether's theorem, to be connected with conservation of momentum. And so the fact that when you change your axes, the physical laws don't change, turns out to have a really deep meaning to it. Now, that may seem really strange, because of course the physical laws shouldn't change when you move your axes. But it goes deeper. You can set your time any way you want. You can set time equal to 0 at any moment you wish. It's equivalent to resetting your stopwatch. Well, again, Noether's theorem tells us that because the physical laws don't change when you reset your stopwatch, that's deeply connected to conservation of energy. Now, this may seem silly, maybe even ridiculous. Of course, physical laws don't depend on where and when we measure them. But that's really the point of Noether's theorem right there. It tells us that if energy and momentum weren't conserved, then we would live in a very strange universe indeed, where physical laws changed depending on where and when you measured them. What we're going to be talking about in this unit is momentum. Momentum is useful in all kinds of situations, but where it's really useful is when you're trying to analyze collisions. So before we go on, let's talk about what a physicist means by collision. And as with so many other things, the physicist's definition of collision isn't quite the same as the everyday definition. A physicist means a short duration interaction between objects. Note I've put short duration in quotation marks. So these cars crashing together here, that's what you would think of as a collision, and a physicist would agree, because the cars are only interacting for a split second during which they smash into each other. But lots of other things are collisions that you wouldn't normally call collisions. For example, when you kick a soccer ball, It may seem instant because it happens in the blink of an eye, but it isn't instant. It takes a short amount of time for the kick to happen. Your foot comes in contact with the ball compresses as the forces between the foot and the ball get larger, and eventually the ball rebounds and leaves contact with the foot. A gravitational slingshot is also an example of a collision. According to a physicist's definition, the spacecraft and the planet initially are exerting very little force on each other, but as they get closer, the gravitational force gets stronger and stronger until closest approach, and then it gets weaker and weaker again. And so there's a duration during which that interaction is happening. Now, unlike the car and the soccer ball, where that duration is a split second, for a gravitational slingshot, it can be weeks long. But on the time scale of the orbits of the planet and the spacecraft, which could be years or decades long, that really is short duration. But what all these have in common is that the force between the objects involved in the collision is varying during that interaction. And it's that varying, which we would find difficult using the methods we know, that's going to make momentum really useful here. So we need a way of dealing with these changing forces. And because physicists are lazy and don't want to deal with any more ideas than they have to, we're of course going to build the way of dealing with changing forces out of the ideas that we've already seen. So we've seen Newton's second law, written this way, and basically you can think of it as meaning that forces cause acceleration. You could think of it another way, though. A force causes the velocity to change, right? That's what an acceleration is. It's a rate of change of velocity, so forces make velocities change. And a change in velocity you can think of as just an average acceleration times a time interval during which that acceleration occurs. So these are going to be our key, and we've seen them. We've seen them both quite a long time ago at this point. So think, if you have changed a velocity of some object, and you now want to change it more, you have two choices. You could use a larger force, so that you cause a larger acceleration. That larger acceleration over the same amount of time is going to cause a larger change in the velocity. But alternatively, you could use the same force, but do it for a longer time. And of course, you could do both. So notice that changing the amount of time during which you apply the force has an equivalent effect to increasing the force. Let's be slightly more concrete. Let's say you have a cart, a nice low friction cart, and so there's an upward normal force and a downward weight, and we can ignore them because they're going to cancel out, and you pull on it with a 2 Newton force. And let's say you do that for 3 seconds. We know how to analyze this situation. This is a nice simple case. That 2 Newton force on the 1 kilogram object is going to cause a 2 meter per second squared acceleration. And carrying that out for 3 seconds will cause a change in velocity of 6 meters per second. So we could have done this weeks ago. Well, notice that if we instead apply a 1 Newton force, so that we get a 1 meter per second squared acceleration, we can get the same change in velocity if we just apply that force for 6 seconds instead of 3. So we've got the same net effect, the same total effect due to this force, a 6 meter per second change in velocity on this 1 kilogram object. So even though the forces are different, they've had the same total effect because we compensated for the lower force by applying it for a longer time. So we're going to call this total effect, which is the force times the time, the impulse. Those two situations I just described used constant forces. And so you should be objecting, wait a minute, Geoff, you were going about this because we want to deal with changing forces, but you're using examples with constant forces. What's up? Well, we're actually going to use another idea we've seen before. Remember this idea of average. So for example, way back we talked about this bank balance and how you can think of a constant rate of change of your bank balance, but what really happens is that your bank balance doesn't change except on payday, it jumps up suddenly. But it has the same effect as an average rate of change. And we also saw that an area under a v versus t graph always gave you a displacement. And even if the velocity was changing, you could still use the area under the v versus t graph to get a displacement. And this is just related to the idea that this area can be thought of as equivalent to a rectangle where it's the average velocity that you're using instead of a bunch of different velocities at every different time. So we're now going to use that same idea, but we're going to use it with forces, which are causing changes in velocity, instead of velocities that are causing changes in position. Our first intuitive idea, based on the idea that changing the force was equivalent to changing the amount of time during which you apply the force, was that the impulse, which is the total effect of the force, is the force times the time. Or a little more precisely, since this was really based on the average acceleration, this should really be the average force here. Well, just as we did for displacement as an area under the velocity versus time graph, we can replace this idea with our impulse as an area under the force versus time graph. So if you have some complicated force versus time graph like this, it has some area under it, and that's equivalent to a rectangle with a height of f average and the same duration. And because those have the same area, they're the same impulse, and they'll have the same effect on the object. So next time we're going to use this idea to calculate some things. And for example, we're going to be able to calculate something that we actually sort of encountered a long time ago and brushed under the carpet. Remember, with projectile motion, the whole reason we can't set our VF as 0 is because the collision of the projectile with the ground is so complicated. Well, we're going to start off next time looking at a ball bouncing off of a floor, exactly that sort of complicated situation. And with impulse, we're going to find that we can deal with it actually fairly easily. So stay tuned, and next time we will calculate how fast a ball is going after it bounces off of a floor.